Imagine trying to teach a rookie athlete how to play tennis, but every time they miss a swing or take a clumsy fall, it costs you thousands of dollars. That is exactly what it feels like to teach an artificial brain how to work a machine in the real world. If we want to teach a car to drive itself, we can't just put it on a real road to practice. Covering every possible pothole, rainstorm, and weird traffic pattern would take an entire fleet of cars driving nonstop for hundreds of years. Plus, the physical world is unpredictable. You wouldn't want a car taking its very first guess at how to navigate a busy intersection while a real person is walking across the street. Relying solely on asphalt and rubber is far too slow and risky. Trial and error is a terrible way to learn when the stakes are this high. So engineers build a virtual bootcamp instead. They create a detailed digital world governed by the laws of physics, where a robot brain can safely crash 1,000,000 virtual cars without denting a single real bumper. Recreating the wind, rain, and gravity of our physical world down to the millimeter takes a massive amount of math. A standard desktop computer would lock up trying to calculate all of that. That work happens inside data centers, using racks of specialized computers. These NVIDIA systems provide the raw muscle needed to bring these worlds to life. These machines use chips that excel at doing many things simultaneously. Instead of driving one virtual car for 10 years, the computer drives 10,000 virtual cars at once, squeezing a decade of experience into a single afternoon. Without this heavy-duty hardware foundation, simulations could never reach the scale needed to teach a vehicle how to survive the actual road. But there is a catch. If a robot learns to drive in a flawless video game, it often panics when its tires touch actual pavement. Engineers have to account for this mismatch between the screen and the street. The first problem is how the surfaces touch. On the left, a digital road is mathematically smooth, but on the right, real asphalt is messy, creating tiny, unpredictable slips that a robot isn't expecting. The second problem is fuzzy data. Virtual cameras see the world in perfect clarity. Real cameras have to deal with blinding sun glare, sudden shadows, and splattered mud. The spinning lasers and glass lenses mounted on top of a car are complex, and they are constantly battered by the weather, making the information they gather a bit noisy. If we train our artificial drivers in a pristine, perfectly predictable world, they will fail the test of a chaotic, unpredictable reality. To toughen up the artificial intelligence, engineers use two distinct strategies. They inject both precise measurements and extreme chaos directly into the virtual bootcamp. The precision comes from measuring the real thing. Engineers record the exact grip of a real tire on real pavement and plug those exact numerical measurements directly into the simulation's code. The second strategy is to flood the simulation with chaos, effectively shaking up the scenery. This acts like a digital stress test, rapidly changing the lighting, dropping snow, or even warping how gravity works. It forces the car to handle anything, rather than memorizing one perfect route. They even intentionally break the car's virtual vision. By layering thick static and blur over the digital cameras, the AI learns to safely navigate even when it can barely see. Because out on the physical roads, sudden whiteouts are real. The car needs to know how to react when its cameras are overwhelmed. Grounding the simulation in precise measurements, while constantly throwing curveballs, forces the robotic brain to develop generalized survival skills. Eventually, the virtual training wraps up, and the robot brain is downloaded into a physical car for its first trip on the actual streets. But no matter how good the simulation is, the car will eventually encounter something new, like an unmapped patch of loose gravel it has never seen before. This flowchart shows how the car relies on instant reflexes. When the car feels its tire slip, the brain receives that signal and adjusts the steering and brakes in milliseconds to keep the vehicle stable. These instant self-corrections serve as a safety net, allowing the car to survive the initial shock of an unknown situation. A successful trip on the road actually triggers a much bigger cycle of improvement. As the car drives away, its cameras and lasers vacuum up all the messy data from that encounter with the gravel. That fresh data is sent back to the data center, straight into those massive servers to be processed. Engineers use that information to update the virtual bootcamp. The next time the digital fleet trains, they will practice against a digital replica of that exact same gravel patch. These systems aren't just simulating driving, they are speeding up the evolution of experience. By bridging simulation and reality, we are building the safest drivers the world has ever seen.